Have you ever mixed two liquids and just wondered what's really happening on a molecular level? Sometimes they mix and behave exactly like you'd think they would, but other times they can do some pretty surprising things. Today, we're going to find out why. My name is Sourabh Kaushik, and in this explainer, we're diving deep into the world of chemical solutions. We're going to look at why some mixtures play by the rules and why others, well, they like to break them. And we'll be doing it all based on the concepts right out of your NCERT Class 12 curriculum.
So here's our game plan. We'll kick things off with the so-called perfect ideal solution. Then we'll get into the real world and see how most solutions actually deviate from that. After that, we'll check out a really cool exception called azeotropes, and we'll wrap it all up with a quick review. Sound good? Let's jump in.
All right, first up, let's talk about the theoretical gold standard, the ideal solution. You can kind of think of it as the perfectly behaved student in the chemistry classroom. It follows every single rule, no questions asked.
So, what's the rule book for these perfect solutions? It's a thing called Raoult's law. Basically, this law predicts the vapor pressure of a mixture. It says that the more stuff you have of a certain component, that's its mole fraction, the more it's going to contribute to the total pressure. For an ideal solution, this prediction is spot on every time.
So what actually makes a solution ideal? It really boils down to three key things. First, the forces between the different molecules, let's call them A and B, are pretty much identical to the forces they had with themselves. Because of that, second, there's no heat change when you mix them. No heat gets released, none gets absorbed. And third, the volumes just add up perfectly. You mix 50 milliliters of A and 50 milliliters of B, and you get exactly 100 milliliters. No surprises.
Now, while a perfectly ideal solution is more of a theoretical concept, some mixtures in the real world get incredibly close. Take N-hexane and N-heptane, for example. These molecules are so similar in size, shape, and how they behave chemically that they can mix together almost, well, perfectly.
Okay, so that's the perfect world scenario. But what happens in the real world? Well, that's where things get a little messy and honestly, a lot more interesting. Let's talk about non-ideal solutions.
And here's the thing you've got to remember. Non-ideal behavior isn't some rare exception. It is the norm. Most solutions you'll ever work with don't follow Raoult's law perfectly. So understanding how and why they deviate is absolutely crucial.
And when they deviate, they can go one of two ways. A solution can show positive deviation, which means the vapor pressure ends up being higher than you'd expect. Or it can show negative deviation, where it's lower. Let's break down what's happening in each case.
Let's start with positive deviation. The name itself is a great clue, right? Think positive as in more. More vapor pressure, which means the molecules have a higher tendency to escape the liquid.
This happens when the new attractions between the different molecules, A and B, are actually weaker than the bonds they left behind. You could almost say the molecules don't like each other as much in the mixture. And because those new forces are weaker, it's way easier for them to break free and escape into the vapor phase.
This leads to three main consequences. First, as we said, a higher vapor pressure. Second, the mixing process is endothermic, which means it actually absorbs heat from its surroundings. That makes sense, right? You need to put energy in to break the stronger old bonds to form weaker new ones. And third, the total volume actually expands a little, since the molecules aren't holding on to each other as tightly. A classic example of this is mixing ethanol and acetone. In pure ethanol, you have these really strong hydrogen bonds holding the molecules together. But when you introduce acetone, its molecules kind of get in the way. They wedge themselves between the ethanol molecules and disrupt those powerful bonds. The new interactions are weaker, and boom, you've got a classic case of positive deviation.
Now let's look at the flip side, negative deviation. And just like before, the name tells you the story. Think negative as in less vapor pressure, because the molecules are holding on to each other much more tightly. This is the complete opposite scenario. Here, the new attractions that form between molecules A and B are actually stronger than their original bonds. They like each other even more in the new mixture. This stronger grip makes it much harder for them to break away and escape into the vapor phase.
And again, we see three clear consequences. First, the vapor pressure is lower than predicted. Second, the process is exothermic. It actually releases heat. Why? Because forming these new, super strong bonds gives off energy. And finally, the total volume shrinks a bit,
as those stronger attractions pull all the molecules closer together.
A perfect example of this is mixing chloroform and acetone. My name is Sourabh Kaushik, and this is a classic example in chemistry. On their own, the forces are weaker, but when you mix them, the hydrogen atom on a chloroform molecule forms a brand new, strong hydrogen bond with the oxygen on an acetone molecule. This powerful new force pulls them together, which releases heat and drops the vapor pressure.
Okay, so what happens when these deviations from the ideal path get really, really big? Well, something totally fascinating happens. We get something called an azeotrope.
So what on earth is an azeotrope? It's a special mixture that, at one specific composition, basically acts like a pure substance when it boils. The liquid and the vapor have the exact same makeup. This is a huge deal for chemists because it means you can't separate the components using simple distillation anymore. It's the reason why it's so hard to get 100% pure ethanol from a water mixture.
And this ties right back to what we were just talking about. Solutions with a really large positive deviation, like our ethanol and water example, form what's called a minimum boiling azeotrope. That means the mixture actually boils at a temperature lower than either of the pure liquids. And on the other side, solutions with a large negative deviation form a maximum boiling azeotrope, which boils at a temperature higher than either component.
Phew! Okay, we have covered a lot of ground. So let's just pause for a second and pull everything together with a quick side-by-side comparison. This should help lock it all in. This table really lays it all out. For an ideal solution, everything is in perfect balance. It follows Raoult's law, there's zero change in heat, zero change in volume. For positive deviation, you get weaker interactions, which leads to higher pressure, heat being absorbed, and expansion. And for negative deviation, you have stronger interactions, resulting in lower pressure, heat being released, and contraction. See, it all comes back to how strongly those molecules interact.
And that kind of leaves us with a final thought to chew on. We've seen how even simple two-part mixtures can act in really complex, non-ideal ways. So what does that tell us about the ridiculously intricate chemical systems that make up everything from our oceans to our own bodies? The real world is profoundly non-ideal. And you know what? That's exactly what makes it so fascinating.
I really hope you enjoyed this deep dive. If you found it helpful, do me a favor and hit that like button and subscribe to my channel, Sourabh Kaushik, for more explainers just like this one. Thanks for watching.